based on your document. EM22, Electronic Properties of Superconductors. Lecture, Electronic Properties of Superconductors. Course, Condensed Matter Physics, Functional Materials. Duration, 1 hour. Instructor, Dr. A.S. Learning Outcomes. By the end of this lecture, you should be able to understand the phenomenon of zero resistance and perfect diamagnetism in superconductors. Comprehend the Meissner effect and the role of London equations. Differentiate between Type 1 and Type 2 superconductors. Appreciate the foundation and implications of BCS theory. Recognize the significance of high-temperature superconductors and their applications. 1. Introduction to superconductivity. Let us begin with the historic discovery of superconductivity. In 1911, Heike Kamerlingh-Onnes observed that mercury, when cooled to 4.2 K, exhibited zero electrical resistance. This resistance-free state is called superconductivity. Two key properties define superconductors: zero electrical resistance below a critical temperature, Tc, perfect diamagnetism, they expel magnetic fields completely from the interior in. This second property leads us to the Meissner effect, which we'll soon explore. Figure 1. A typical resistance versus temperature curve, showing a sharp drop to zero resistance at Tc. 2. Meissner effect and perfect diamagnetism. In 1933, Meissner and Oxenfeld discovered that superconductors not only conduct without resistance, but also expel all magnetic fields from their interior when cooled below Tc, irrespective of their magnetic history. This is the Meissner effect. London equations. To describe this, the London brothers proposed frac 1 lambda in frac 1 math b, where math b, magnetic field inside the superconductor, lambda L, London penetration depth, a measure of how far magnetic fields penetrate the superconductor. This is not just classical behavior, it signifies a new quantum state of matter, coherent, collective, and highly stable. Figure 2. Diagram of the Meissner effect showing field lines being expelled. 3. Types of superconductors. There are two main types. Type 1 superconductors. A single critical magnetic field, Hc, show an abrupt transition to the normal state, typically soft metals like PbHg. Type 2 superconductors exhibit two critical fields, Hc1 and Hc2. Enter a mixed state where magnetic flux penetrates in quantized vortices, include high-temperature cuprates and metallic alloys like MbTi. Figure 3. Magnetization versus magnetic field plots clearly differentiate the two types. 4. BCS theory and the energy gap, 15 min. In 1957, Bardeen, Cooper, and Schrieffer formulated the BCS theory. Electrons in a lattice can form weakly bound Cooper pairs via phonon interactions. These pairs act like bosons, allowing them to condense into a ground state with zero resistance. The formation of Cooper pairs introduces an energy gap, delta, at the Fermi surface. Delta T equals delta 0, square 1 minus frac TTC. This gap can be detected experimentally in specific heat anomalies, tunneling conductance, e.g. Josephson junctions, infrared absorption. Figure 4. Energy diagram showing gap formation at the Fermi level below Tc. 5. High temperature and unconventional superconductors, 10 min. The landscape changed in 1986 when Bednorz and Miller discovered cuprate superconductors, like YBA2 Cu3O Lathud or YBCO, with transition temperatures above 90 K. Characteristics of high Tc materials, strongly anisotropic and layered structures, exhibit complex phase diagrams, not explained by conventional BCS theory. Other notable unconventional superconductors: iron-based superconductors, MgB2, transition at 39K, applications, MRI magnets, maglev trains, squids for sensitive magnetic measurements, quantum computers, energy storage and transmission lines. Figure 5, a timeline or bar graph of Tc values for various superconducting families. 6 summary and takeaways. Let's conclude the session. Superconductivity is marked by I0 resistance and the Meissner effect. London equations explain magnetic behavior. BCS theory describes quantum pairing and energy gap. Type 2 superconductors with mixed states are key to practical technologies. High-temperature superconductors are a class of materials with extraordinary applications and rich physics, still being explored. References 1. Tinkham